Well, good afternoon, David, John, Kelvin, and Pacific Partners. Wait a minute, David, where did you go? In any case, it is summer, and in a lot of places it's pretty nice outside, so I appreciate you all being interested enough to sit in this afternoon. I hope we can make it worth your while. We're going to take a look at something that's been a real curiosity for me since we bought our plug-in hybrid electric car back in 2018. And the question is, everybody's wondering what's going to be the effect of these things on the grid. And the fact of the matter is, if we play our cards right, electric vehicles not only can be good for the people who drive them. I mean, I love driving the car. It's really a very nice machine. Uh, but in addition to being good for environment, uh, a lot of other things like that. They can be good for the grid. And so we want to take a look at that today. I decided that it's about time I start looking at some numbers and see where we might be in another 10 or 15 years. And so since we only have four folks listening in today, I think we ought to make this as informal as possible. So feel free to either leave your mic open if you don't have any background noise, or if that's the case, or if there might be any echo, leave it off. But otherwise, if you have a thing you want to add, ask, or whatever, the answer to the question would be either an answer right away, or that we're going to cover this later, or I don't know yet. And there's still some stuff out here that's not really known. So David and John, I see okay, good. So check your mic, make sure it comes on, and just uh, let's get a little idea of what the backgrounds are. We can maybe do a little shortcutting if we know what everybody does in the engineering field. David, could you start since your mic is on? Tell us a little about yourself. What's your background? What are you currently working on?
Um, I'm a retired engineer after working 34 years at Eastman Chemical Company. And then I partnered with a small local solar firm and did kind of their sales and one-line drawings and their engineering and structural letters for about 80 solar installs. And also have a passive solar house and solar PV and have been driving electric vehicles now for 15 years and probably racked up about 260,000 gas-free miles.
Wow, that's fantastic, Dave. In fact, the way you talk, you sound like you could be my twin brother. I reviewed about 50,000 watts of residential photovoltaic plans this morning before we got online here. Kelvin, how about you?
Yeah, good morning. I'm a retired engineer from Edison here in Southern California. My main interest is one of my main tasks as an engineer was to help stabilize the grid for Edison. And one of the hard ideas when I left, I retired this year was this idea of bringing in the electrovoltaic cars into helping for stabilizing the grid. So since I'm planning to continue doing business as a consultant, I thought this would be a good idea for me.
Well, I mean, I kind of like that idea. I'm going to have my 82nd birthday this summer, and I've been in consulting and kept my PE up to date. And it's a whole lot more interesting than sitting out and getting sunburned. I can tell you that. Uh, and I live in South Florida, so the opportunity for a sunburn when it's not raining is pretty good when it's almost directly on me. John, can you unmute? Tell us a little about yourself.
Yeah, I'm also a retired engineer. I worked in 32 years in the utility, well, no, 32 years in my last employer in the utility industry. And I consulted for 3 and 4 years, but basically I'm a useless eater now. So
Yeah, and by the way, you're going to see some references to Edison and their estimates on EV populations here. So Edison Electric has certainly made their mark in EVs. And Pacific Partners, who might that be? Can we assign a name to that? And are you really out there on Pacific somewhere in one of those three states? I see you are unmuted, but I don't hear you.
Strange.
Oh, who said strange?
Dave Rivnet.
Oh, Dave did. Okay, yeah. Well, how could the mic be on and the maybe the volume's down somehow? Good question. Well, maybe that's all problem will get solved as we go. But anyway, um, if you look at the backgrounds on these slides, this presentation is actually more than 100 megabytes long because of the photos. I didn't try to reduce their size, so fortunately the PDF is a whole lot shorter. And I'm not sure whether you've ordered up a set to look at for later taking the quiz or not, but when I was going through the slides again last night and this morning, this is the first time this presentation has been given, by the way. I found a couple fairly minor typos that you might come across, so I decided that I'm not going to redo the PDF until we finish today, in case we find any others. So watch for typos and let me know if you see anything, okay? I try to clean that up. My job is to review plans. Now we got a t-shirt that says Department of Redundancy Department, but it seems like it takes forever to make sure that every typo is gone, regardless of how much AI might be there trying to tell me it's not right. Okay, so let's move on here. Why do we need to store energy? And I don't imagine, given the background of y'all, this is probably no particular surprise. Wait, did somebody new come in? We had four. Who didn't get a chance to introduce themselves? I'm sorry I missed that. But the person who did not get a chance to introduce yet, feel free to open your mic and tell us who you are and what you're doing right now. See if you're retired like the rest of us. Pacific Partners mic is on, but no sound there. Kevin Estrada. Kevin, are you the new guy?
Kelvin. Nope. Kelvin, like in degrees Kelvin.
I'm sorry, what was that?
The name is Kelvin, like in the temperature scale.
Kelvin, sorry, yeah.
No, I'm not the new guy.
Okay, well, let's move on here. And like I say, if you see anything that you want to talk a little more about, just speak right up. Just say, "Hey, Roger," and that gets my attention, and we'll see what you want to talk about. Okay? So, well, why would we want to store energy? Well, some energy sources operate best if run at a constant power output. You probably know which ones I'm talking about. Nuclear, if you run that anything other than what it likes to be run at, it's not happy. So nuclear was the first reason why we started getting serious about energy storage when we started pumping water uphill about 60 years ago. So that's one reason. And of course, then there's this thing called the sun. And since the energy source is free, it's kind of silly not to try to collect all the energy it'll possibly generate. But then again, if you're going to collect it, you got to do something with it. So then those of you with the utility background know that the overall load to the utility system is not completely predictable, although it's predictable more or less within about 2% from day to day, and that's amazing. But that's because of the aggregate load. But neighbor to neighbor, we do get this smoothing effect by people not using everything exactly at the same time, except during peak times when people tend to use certain appliances and peak out. And the output of some energy sources has some level of uncertainty. And of course, that's your sun. Certainly, it's not going to shine at night, but when the clouds affect it, then the intensity goes down a bit. And the wind blows when it feels like it. Well, I suppose there's a little more effect to it to that, atmospheric pressure differences and things like that. But still, we don't necessarily get it to blow when we would like it to blow. And a lot of times when we wish it didn't blow, it ends up blowing. So wind is one of those things too that very useful when it's blowing at about 18 miles an hour. And we're certainly doing our best to make use of it. But that's not necessarily when we want to use the electricity. One thing that's happening, and I wouldn't be surprised you're all aware of it, there were very close to 20% renewables on the grid right now, if you include hydro. And I mean right now, 2025. And this is not just the United States either. There are a lot of other places that are even further ahead than us. I'll go somewhere like Costa Rica or Iceland, and they're almost 100% renewable. And Norway's up pretty close, so a lot of hydropower and wind power in places like that, and even things like all those hot springs and hot geysers up in Iceland.
Roger,
Yeah,
Dave, um, I just looked at the EIA numbers and we're at basically 20% for just wind and solar. You add hydro in and we're at 26% renewable.
exactly. And if you want to talk about carbon free, you can throw in the nuclear. I mean, I'm
Correct.
not, I'm neither a nuclear advocate or opponent. Because nuclear is riding now in terms of new nuclear, it's looking at pretty expensive. So it's amazing how economics are a driving force, and we're going to be talking a lot about economics today as whether or not these ideas that I'm going to throw out are practical. So
So,
yeah, I appreciate you sharing that information.
so you might want to change that 20% to 26 because you say including hydro.
Oh yeah, okay. All right, I will change that to 26%. Yeah, this is probably a 2023. Well, no, 2025, but and in fact, 2025 has exceeded the expectations that were on the table in 2023. So that's always a nice thing. Whenever we're talking about good things, if you get more good things than what you were thinking you were going to get. Everybody knows peaking power is really expensive because the fuel is pretty expensive, and then the other part of it is you don't turn those on for more than the duty cycle on those maybe says 5 or 10% on the real peakers. So if you got to make your money on a power generation source that runs only 10% of the time, you got to charge big bucks for that electricity. So that's another issue that's out there. Fuel costs and just the fact that you got to charge for it because you don't use it very often. Um, Operating large rotating generation facilities at low output is inefficient. Yeah, you got something rotating at 1800 RPM or whatever it takes to, or 1200 or whatever, depending how many pulls on your generator. And you keep that thing going, whether or not it's generating very much electricity, it still requires something to keep it up to speed. So keeping this background power plants online just so you can turn them on if you need them. When they're not online, they are still burning fuel. And obviously, if they're not generating electricity, the efficiency is zero. So that's not very productive either. So if there's a way to fix that, that's nice. And certain loads don't like to be interrupted. You know, if you're on a breathing machine and you lose your electricity, that's not a pleasant experience. On an elevator and you lose power, that's not too pleasant. So, you know, it's kind of nice to have some backup power. Make sure they stay on. And there are times when utility is down and backup power is needed. Of course, that's very, very rare. Um, but it happened. It happened up in Nashville area last year. And my friend Joe and Carol up there, they had uh, about 11 kW solar with 13 kilowatt hours of storage, and they hardly noticed it because it kept going, even though the rest of the utility was down for a week or so. So a little backup power and a little few batteries like that to back up individual places is kind of nice in the time when occasionally the utility might go down. So let's make sure we're up to date on all the terminology, and it's probably not all of it, but everybody knows what watts are. But when you talk storage, you talk kilowatts, megawatts, gigawatts, and terawatts. And storage, wait a minute, I thought you stored energy. Well, yeah, it does, but when you get it back, you get it back in a form of power because the energy stored will deliver the power that you need to run your load. And that's the nice thing is that batteries are like rotating sources. They provide what you need at the time up to the limiting output power of that source. Watt hours, that's your storage capacity and energy. And watt hour is a pretty small thing. Kilowatt hour, pretty big thing actually, 1,655,000 foot-pounds. And that's a lot. And then there's megawatt hours and billions of kilowatt hours, which is like a million megawatt hours or a terawatt hour. And then there's quads. And like people like to talk about quads, that's a quadrillion BTUs, which is roughly 293,071,070.17222 megawatt hours. I couldn't resist putting in the 0.17222 because I mean we engineers we love precision and so let's get it as close as we can. And discharge time, it's important to know, is the time it takes to discharge the rated storage at the rated power. Okay, and you know, discharge time, one might argue that, well, you can discharge any longer time than that, but you can't discharge in a shorter time or you damage your source. And highly likely your source is going to be current limited anyway. So then there's the characterizations and ratings. Maximum discharge rate in kilowatts. Maximum charge rate. It could well be the charge rate is different from the discharge rate. We'll see why that is in a little while. And the charging rate is C over X, where C is simply the capacity, the energy capacity, and X is the minimum allowed time to discharge. So C over 2 means that you don't dare discharge this source in anything less than 2 hours from full to empty, whatever empty is defined. Empty might be defined as 10% of empty because a lot of sources don't like to be discharged all the way down to zero. Some are okay with it, others don't like it. Capacity measured in kilowatt hours, energy. 1 kilowatt for an hour is a kilowatt hour. And the useful capacity of storage, the kind that we're using in 2025 is typically somewhere around 90% of the total capacity. And that's because you got to charge it and you got to discharge it. If you charge a DC battery with AC and discharge a DC battery and convert it to AC, your overall round trip efficiency is about 90% with lithium. Lifetime cycles, that's simply defined as a cycle defined as 100% to minimum capacity and back again, okay? And the question is, how many of these lifetime cycles can you get? 3,000, 5,000, 10,000? And generally the manufacturer will tell you that. Or the manufacturer now is becoming more common to say, we will guarantee a certain amount of lifetime storage in total kilowatt hours over the life of the product. And that's simply the useful capacity times the number of lifetime cycles. And when again, the lifetime cycle is considered to be a complete cycle from completely full to the minimum allowed capacity. Okay, so some useful terms as we move through, and these are generally applied on a daily basis. Because you can fill up a battery in a couple hours maybe, and discharge it in a couple hours maybe. And if you do that, then you could do that 6 times a day. And 6 times what you get in 1 hour would be what you get in a day. And then do that for the number of cycles. So in any case, the depth of discharge percent is a useful number. Round trip efficiency in percent is a usual number. And usually it's measured as AC to AC in anything that's going to be grid supported. Some more terminology. Storage duration. There's short storage, medium storage, and long storage, depending whether you want seconds, minutes, or hours of regulation or replacement of energy from other sources. And what is storage useful for? Well, I mean, these are mostly obvious things: backup power during grid outage, voltage stabilization for the grid, frequency stabilization for the grid, load leveling for the grid, provide peaking power, short-term backup for primary source failure, and transmission and distribution deferral. Now there you can get in some good money, because if you don't have to build additional transmission or distribution, you can save a couple of bucks. And if you can use your distribution system with storage, if you run electricity backwards in the distribution system, it becomes transmission system at a lower voltage. So that's interesting. So storage has its uses, as several of you have already observed. Energy storage technology is a lot of it. The oldest is, batteries, but then pumped hydro is the oldest large scale. Batteries, whether they're in motion or whether they're not moving, they still store energy. Molten salt's very popular for solar thermal systems, where you heat a salt really, really hot and then store it hot and then use it in a steam generator overnight to make electricity at night when the sun is not shining. They're working with that a lot on California. They've got them to the point where they're reasonably cost effective. They're doing these in other hot desert areas as well. Supercapacitors, compressed air, not much compressed air, only really 2 big systems in the whole planet, but it's out there in a commercial fashion. Flywheels, pretty neat. They get up to a megawatt worth of spinning steel, and hydrogen is common energy storage technology that can be used either as a fuel after you make it. Burns pretty clean, just turns into burn hydrogen, you mix it with oxygen, you get water, no CO2 there. Although water is a greenhouse gas, but it's not quite as long lasting as CO2. Superconducting magnets, weightlifting, and so forth. We're going to focus on the batteries. So what are we looking at for U.S. future energy storage needs? Because if we're thinking about storage, we might as well think about what we're going to need. And in doing this, we need to distinguish between the daily needs and the annual production, because we talk about annual energy production and annual energy use, and usually that's on the basis of the primary sources. But then our energy use is on a daily basis, and our storage is on a daily basis. So we need to make that distinction as we talk about quantities of energy. So make sure we all understand that right away. It's pretty obvious. Like we said earlier, a 10 kilowatt hour battery depending on its discharge and cycling rate, it can deliver 10 kilowatt hours a day or less than kilowatt hours a day. But in 365 days, then it could very well deliver 500 kilowatt hours. Now, in order to deliver 500 kilowatt hours, of course, it's going to have to take into account the efficiency. You're going to have to charge it up with 5,500 kilowatt hours. But that's better than curtailing the source if the source energy is free, provided that the economics are favorable for the storage mechanism. So it is also important to note that the storage element exists to provide instantaneous power to a load when the load needs it. And just like your battery, depending on what kind of flashlight you connect it to, it's happy to provide whatever electricity necessary, unless that bulb is way too low resistance, and then all the energy dissipates in the internal resistance of the battery. There's a limit to what that battery is willing to do, and that affects the discharge rate. You can buy either power or energy or both. If you're on a commercial rate where you've got a monthly demand and then a kilowatt hour rate. My building here, our monthly demand charge about 12 bucks a kilowatt, and our kilowatt hour rate is about 8 cents a kilowatt hour. And that's the electricity that's charging my electric vehicle at 8 cents a kilowatt hour stuff, because I try to charge it off peak. So our friends at National Renewable Energy Lab confirmed that future energy needs depend on a lot of things. Wow. That's pretty profound, isn't it? Would you have ever imagined? Okay, anyway. This is what NREL predicts as the power generation capacity requirements from 2020 to 2050. All right, and notice there's pretty quick jump between 2025 and 2030, and then it kind of levels off a little bit, almost becomes linear. Might expect it to become exponential, but then again, maybe not. Maybe there are other factors in there that keep it more or less linear. In fact, maybe it would even level off if we predict this thing out to 2070 or something like that. But 2050 is good enough for me. I don't expect to be here then anyway. Somebody else is going to have to check to see whether this is right. And this isn't really my prediction anyway. It's summer peaking requirements as anticipated by the folks at Statista. And by the way, feel free if you are interested in these slides. Um, everything is documented where it came from. And I would consider it a compliment if you thought it was interesting enough to show somebody else. So don't be afraid to share this stuff. I consider it my job to come up with ideas, and if somebody else likes it, that's all better. So this is summer peaking power. But then again, in the spring and in the winter and the fall, we don't need all that much capacity. But it's there, sitting idle, in order to be able to meet the summer peak. Okay? So that says something about when we use our electricity and what we require as our generation capacity and how storage can fit into that equation. Here is the anticipated needs of annual megawatt hour generation. Okay, and the black squares are total generation from all sources. And the green ones are total generation from all renewable sources. And notice how these are all on the same scale, nice linear scale in billion megawatt hours. Notice how the black squares go up at almost the same rate that the green ones do. In fact, a little bit slower. The black increases from 4 to about 5.5. The green increases from about 0.8 to about 2.1. So that's at least a factor 2.5 increase in storage available, generation available from renewable sources, and an increase of only about 50%. No, wait a minute, 4 to 5.5 is more than 50%. But the percentage increase in total kilowatt hours uh, is less than the percentage increase for renewable sources. And how is that happening? Might ask. So we'll take a look in a minute and see where we're headed with that. This is the good old United States Energy Information Administration. Lots of good data they collect. If we compare the annual gigawatt hours to gigawatt capacity, that's interesting. In 2025, the gigawatt hours anticipated are going to be 4.3 times 10 to the 6, and gigawatts 1200. So that's 0.4, 40%. In other words, we are only using 40% of what we could have used if we were running at full capacity all the time. Of course, that's good because it gives us time to take down the nuclear plants for a little maintenance, take down the other plants for time for maintenance in the spring and the fall when we're not using all that capacity. So in any case, our capacity factor right now, 2025, is about 40%. So we're effectively generating 2.5 times more than we use on average. But just to make sure, or we have the capacity to generate 2.5 times more than what we use on average. Okay? Between 20 and 2050, here's what the picture looks like based on NREL predictions. Going down. Well, why is that? Well, guess what happens? If you're going into renewable sources like solar, you don't get 100% production out of that, do you? I mean, it does pretty well in the middle of the day, but at midnight it doesn't do too well at all. So its average capacity factor on solar is somewhere around 30%. And so that's what we're dropping towards is the renewable maximum capacity factor is somewhere in the neighborhood of 30%. But once we're there, that's it. It levels off there because the sun is pretty much going to behave the same for about the next 4.5 billion years or so. So therefore, once we have the generation capacity, the fuel source is going to keep us at about that capacity factor for a long, long time. And what does that mean? Well, that means the amount of storage will depend on what the summer peaking is going to be. So if we have a way of limiting that summer peaking, we can maybe level off in the amount of storage we need at some point as well. So interesting observations. I've been wanting to do this calculation for a long time, and it is very interesting. And in fact, for an old guy like me who wants his great grandson to have a life in the year 2100, this looks encouraging. So here's the big question. How much of the additional power and energy will need to come from storage? What storage mix will be the best mix? So in the process of making this decision, we're going to need to keep in mind that both power and energy both come from primary energy sources. So what do these primary energy sources look like? What have they been and where are they going? Let's take a look at that. And so here we have a picture of worldwide consumption by primary energy source. That means that all the coal you burn into if we turn that coal into electricity, only about 35, 40% of that primary energy becomes electrical energy. Okay, so that's pretty significant. The important thing is to look at this green line because that's your renewables. That's what we were talking about earlier about how quickly it's going up. Notice we have a log scale on the vertical scale. So that 100 quads mark, it looks like the renewables are going to hit the 100 quads before 2030. if they keep their historic growth rate. And this is worldwide, by the way. So, by the way, whatever we decide about whether we have to burn more fossil fuels in the United States, the Chinese aren't going to make that decision. They know the economics. The people in India aren't going to do that. The people in the European Union aren't going to do that. We're the only guys who are claiming that the fossil stuff is the good stuff. So, and not necessarily everybody in this country believes that either, but there are a few people who are saying that, and unfortunately, they're not with the trend in the rest of the world when they say that. And here's your proof of what's going on. Notice that hydro's going up a little bit, and it may well go up more than that because the Chinese have some ambitious plans for some hydro plants. We'll see what happens. But solar, that's a lot easier for siting and other things and is predictable. So I look out my window, and there's an awful lot of rooftops out there, and there's an awful lot of other places, parking lots, canopies. There's a building next to me that could easily put about 200 kilowatts on top of their parking canopy, for example, and it's not there yet. So um, will we be there by 2030 where all of the fossil sources will be in the process of being replaced by other sources? Good question. But you can see the trends, and it's very interesting to take a look at these trends and do a little guessing. After all, we're allowed to do that. Anybody's allowed to guess. These are the numbers specifically for 2023. Okay, and people who do this, and notice the no CO2 sources in 2023 were 18.7%. And this is worldwide, 18.7%. We need to remember, what are we doing in the United States versus what are we doing worldwide? There are some places that are not as clean as we are, but there are other places that are a lot cleaner. There's still a lot of coal in China, no question, but they're replacing it. And anyway, it's interesting. This is British Petroleum statistics. They're the guys who've been keeping track of this. And back, you may remember, back in around the year 2000, BP actually had a solar division. But that was back when solar was not very profitable. So they kind of gave that up. But now a lot of the fossil people are starting to look that way again. The Energy Institute is a group that took over for BP, so the most recent data is from the Energy Institute. So you may need to look up both of these sources. If we look at the NREL estimates of total energy storage in gigawatts and gigawatt hour estimates, they look like this. And this is, gigawatts of storage. Not annual use, but this is what's there that can be used today. And like a 100 gigawatt hour battery storage system out in the middle of the solar field, something like that. So it's got 100 gigawatt hours, and you use it relatively quickly as opposed to taking a whole year to discharge. So notice that it's interesting, partly because the green stars are the gigawatts. That's the actual power production. The gigawatt hours, the storage goes up faster. Why would the storage go up faster than that? Well, the reason is because we're starting to build bigger storage capacities rather than 2 hours worth of storage, which is kind of typical for some of these larger fields of, hundreds of megawatt type energy storage system. They'll maybe only have 129 megawatt hours, which is like 1.29 or 1.3 hours of storage at 100 megawatts. But we are starting to build bigger ones, and we're talking about what NREL uses is 2 hour, 4 hour, 6 hour, 8 hour, and 10 hour storage. And as we approach 2050, the longer storage systems are anticipated to be, they'll build more of them. So therefore, the storage goes up. So gigawatt hours. somewhere up in the neighborhood of 2,400 by 2050. Okay, number to keep in mind. Now, this is NREL's most ambitious scenario. Okay, it's optimistic. It's 2, 4, 6, 8, 10-hour storage elements and so forth. Yeah, but these gigawatts and gigawatt hours are available every day and maybe more than once a day, even if we needed them more than once a day. Okay, so these are net discharge figures, by the way. Yes, we need to have about 10% more in order to fill them up than we get out when we discharge them. So we keep that in mind as well. On the other hand, the fuel charge is free. Yes, there's a installation charge. But once again, the economics are very favorable. Uh, so,
I'm really don't believe any of these numbers because they're based on, this idea that, they're going to build all these data centers here in the United States when, first of all, I mean, we saw the same thing with the dot-com bubble where everybody was going to have websites and everybody was going to be uh, building web pages to sell merchandise and pets.com and all pet rocks and everything else. But what happened was there was concentration. So now there's Amazon. So a lot of stuff that was never built, a lot of this load or a lot of the web traffic was never built, and there was tons and tons of dark fiber after the dot-com boom. I think you're going to see the same thing here because the utility industry has a history of that. I mean, history was that there was tremendous load growth in the 50s and 60s, and people were building power plants like crazy, and they were going to say, we're going to build hundreds of these nuclear plants that was going to provide energy too cheap to meter. And it never happened and it ended up that there was, nuclear plants get they got dragged, their schedules got dragged out. There was a lot of what they called stranded investment. In other words, nuclear plants that were shut down. The famous WUPS project. And I think it's going to be the same thing here because I think that first of all, there's going to be the same consolidation with AI as there was in dot-com. And also, they're not taking into account that, that the internet makes everything in the world. Why should they build a data center that's going to use all this energy, in Podunk, Kentucky or something like that, when they might as well just build it in China where the electric rates are a third of what they are here. So I really doubt any of these numbers are going to become anywhere near fruition, but because I've seen, worked in the industry, in utility industry long enough to see that, these ups and downs and, things, somebody, I think it was Yogi Berra said, it's very difficult to make predictions, especially about the future. So just saying.
no, no, I mean, you make a really good point because indeed, that's what this growth between 2025 and 2030 is anticipated is all be for all these data centers. And it may or may not happen. Now, what we're doing here today is we're saying, what's it going to cost if it does happen? Is it possible to do it? And obviously, if we don't have to do it, that's even better. So your
Well,
point is well taken. Your point is
but
well
here's
taken.
here's
We
a
may
contrary
not really
point to
even
that.
do it, but if we had to, we're going to show that we probably could and still afford it.
Well, I know that
Um,
a lot of people invested into that Whoops project at Washington State, and they lost all their money. So
Oh yeah,
it's
yeah.
not a matter
That's
of
a
just it'll be great if it doesn't happen, but if people will lose their jobs, companies might go bankrupt. It's
that's true. That's true. Those
it's
five nuclear
there
plants
seems to
up
be
in
a
Washington never got built.
yeah there seems to be a lot of rah with a lot of this renewable stuff, but there's economics and history, needs to be factored in. And like I say, nobody considers, I mean, we saw DeepSeek came out, with basically a bunch of, a dozen or so tech bros in China, made a usable AI system, that uses a fraction of the energy and it's a fraction of the cost. So, um,
No, no, there's no question that as the future comes, technology will progress. And a lot of these numbers may end up being a whole lot smaller. And
I,
yeah, probably some folks will lose jobs and the people, but right now, the job growth rate in the renewable industry is higher than the growth rate in all the rest of the jobs
fossil
rate
fuels.
in the country. So, that's what's happening now. And what's going to happen in 2040? People are going to probably find other things to do. There's always this possibility that we could reduce the work week to like a 30-hour work week, like the people in Europe are doing. And maybe we'll get over this idea that we have to work 70 hours a week. I'd love to get over that. I'd love to try working 30 hours a week someday. Uh, but somehow here in this country, we have this idea that if you don't work all the time, then you're not doing your job, whatever. And the Europeans, in the meantime, are out there drinking beer and having fun, and having 6 weeks of vacation and whatever. So maybe we need to learn something. Maybe we need to put our ear to the ground and do a little listening. Anyway, let's move along and see that.
Oh,
Yeah.
one quick point from
Oh,
Dave
good.
here. I
Yeah.
think we're missing two other potential factors of growth. I truly believe we're going to be seeing a lot more electric vehicles in the future, and we're going to see more and more people getting heat pumps rather than gas furnaces. Matter of fact, last year we installed more heat pumps than gas furnaces for the first time in the history of the country. So I think there's other things that are going on that are going to increase electricity demand besides data centers.
Yeah, absolutely right. Yeah. And that's the point. Data centers are not what it's all about, but that's what we read about. But you're absolutely right. And of course, the other nice and these things that we're buying, they're more efficient. Talk about a hybrid water heater and so forth. But that's subjects of other webinars. Let's focus on the electric vehicle part that you mentioned because that is really interesting. And that's really what we're all about here today. So let's see what we got next. What? What an interesting question. How appropriate that you should mention that right now. Where do the BEVs fit into this picture? Let's do some numbers. Average storage capacity, 75 kilowatt hours, give or take. Some of the Teslas have 100, some of the others have a smaller, but somewhere in the neighborhood at 75 might be an average. And we can assume whatever, and it might be different. Let's assume that we equip these EVs with inverters. Now, why would an EV want an inverter? Well, that's so they can sell electricity back to the grid. And we know that some of the EV chargers are a whole lot more than 5 kW. But then again, we're talking about charging rates and discharging rates. And let's just say that we got a 5 kW discharge rate. And the reason for that is because 5 kW is easily accommodated with a 30 amp, 200 volt, either 208 or 240 volt circuit, and no charging circuit. And IEEE 1547/2018 is simply the IEEE standard that requires these inverters to be nice to the grid, in so many words. So if we do this, make that assumption, then each EV could, we'll assume that every day each EV can spare 2 hours of what it's storing at a rate of 5 kilowatts. And they can do that for 5 days a week. In other words, they're willing to plug in at an opportune time for the utility 5 days a week to help out the utility. All right. If so, what would happen? Now, will people do this? We don't know, but they might if they have enough of an incentive. What it means is each EV can supply 10 kilowatt hours a day. Now, the energy of course, would have to be replaced daily at times when the grid has adequate capacity. Which, rather than at night when the nukes are wanting to generate electricity, may well be between 10 and 2 during the day when the PV wants to generate extra electricity and would like for somebody who's be out there willing to take it. So what I see is charging EVs between 10 and 2 is going to become very popular. Florida Power and Light's already saying that. If you charge your electric vehicle between 10 and 2, you're essentially charging it with renewable electricity. So forget about this nighttime rate, 10 to 2, as we get into a much and much higher mix of renewables into the overall mix. So interesting, 10 kilowatt hours a day from each EV. So that would equate that to a 2-hour storage facility under the definition from NREL. So what are the things when we say about EVs? They get about 3.5 miles per kilowatt hour per automobile. Let's see, we have one gentleman here who's driving his EV for what, 15 years, did you say? Is this about right number for your EV?
Yeah, yes, that's pretty close.
Yeah, that's just about what we get, about 3.5 miles per kilowatt hour. We try to be conservative. We don't try to go 0 to 60 in 2.5 seconds. We try to keep that discharge rate down below a certain amount and accelerate like everybody, well, not everybody, some people like to show off, but we don't like to do that. So in any case, maybe 3 kilowatt hours a day for a pickup truck to drive. The Cybertruck, if you look at the numbers on it, it's 135 hours of storage, and they get about 3 miles per kilowatt hour. 1,000 miles a month, that's 286 kilowatt hours a month, 9.5 kilowatt hours a day. Okay. Solar energy can produce about 120 kilowatt hours a month for every kilowatt up there on the roof. So, in other words, 2.4 kilowatts on a roof can produce enough electricity to meet the needs of the average EV. Okay. I can tell you the average residential installation that we're designing, and we've designed somewhere close, pushing 20,000 now, is about 1,100 or 11,000 watts. Or so, 11 kW, 2.4 kW, and that's almost produces all the needs of the dwelling plus the car. So it's almost a zero energy deal. Very interesting. And it's very convenient if your car can save some of that during the day, if in fact we have a lot of these things on the roof when the utility doesn't need all that power at certain times of the year. So in any case, that means an EV charged with PV electricity, carbon dioxide free electricity, and it can do it for 2 hours a day at 5 kW. Okay. And this is our assumption. Maybe you can do more, maybe less. On average, 2 hours a day at 5 kW, in my mind, is not a bad assumption. So that's 10 hours of grid storage on a daily basis. If we had 100 million EVs, then that would be 1 billion kilowatt hours a day. And that would be 2 hours a day for discharge. That's 1,000 gigawatt hours a day. Now, it doesn't mean necessarily 1,000 gigawatt hours is all going to be connected simultaneously. If it were, we could get 500 million kilowatts out of these things. But the average is probably going to be less. So how does it compare with the NREL estimate? Let's take a look. But first, when are we going to have 100 million EVs on the road? Here's why the Edison Electric Institute made the prediction. We're going to give them the credit on the next picture. And it looks like, bingo, it's going to be right around 2037. They predicted it out to 2035, where we're going to have about 78 million or so. And if the growth rate continues, and when people see these electric vehicles and ride in them and drive them, they want them. And a lot of people that I know, their next vehicle is going to be an electric vehicle. And there's lots of opportunity out here for engineers who are going to be in the business of charging, designing the charging stations for these. So here's your Edison Electric Institute forecast, and it's a good chance we'll have by 2037, we'll have 100 million out there.
I'm curious, where did the electric car usage come from? Because I calculate out that's only like 33 miles a day of usage. And when my son bought his Tesla, the reason why he bought it was he had a 40-mile commute. So, using 80 miles a day, it was a big savings.
Oh
Um,
yeah, I mean, you're talking about
but so I'm
it's
curious about the
equivalent
30.
about, yeah, that's about $1 a gallon gasoline.
Right. So
If
I'm
you're
I'm
using
sort of
electric
curious about
equipment.
the electric car average usage. Is that how did
Oh,
they come up
Well,
with that number? I mean, because the economics of it is the
no,
more you drive, the more you need the electric vehicle. And I think that I've heard somebody here in our group that says has done hundreds of thousands of miles on electric. I haven't done 100,000 of miles on my car, in
yeah,
30
well,
years. So
we've got 37,000 miles on our 8-year-old EV. So,
yeah, that's not a lot.
we bring down the average. No, let's
okay.
take a look at, we've got some
So
demographics here that we'll take a
what,
look at
I
in
think
terms
where
of who
that
drives
number,
where.
this is Dave Rivnak. I think where that number is, the average person in the US is just under 14,000 miles a year. So the average car is 14,000 miles a year.
Yeah,
And if you divide that by 365, you're talking 38 miles a day. So that's pretty close to the average that people are driving. And remember, your son's driving that, but he may stay home on Saturday and Sunday. So those are 2 0 days. He also has days of vacation where he's not driving and, all that kind of stuff. So that gets figured into the averages as well.
yeah. Well, and there's also a lot of people who don't drive that far and still have electric vehicle. People worry about the range of an electric vehicle, and uh, you know, that's another story. We don't really have time to go into all that today, but let's make sure we get to the end. Uh, the assumption here is if we have 100 million EVs on the road by 2037, this is the amount of storage capacity from EVs that could be available at 10 kilowatt hours a day per vehicle. And you compare that to the numbers we've been looking at, and it's pretty big. I mean, it's at 88% of what NREL is saying we're going to need by 2050. That's not realistic, but it's ballpark. I mean, it's what if we only have 20% available instead of 88%? That's maybe a realistic number that we could have people willing to be, and there's even other considerations. But even at 20%, who knows? The number is still of the order of magnitude of what the people at NREL are predicting we're going to need. So interesting. People say, yes, these electric vehicles are going to have a big effect on the grid. We're going to need a lot more generation capacity. Well, maybe not, because if they charge at the time, we've already seen that the capacity factor on the grid is dropping down to about 0.3. So we just have to remember to be charging these things when the capacity is there. And then discharging them when the capacity is not there. And all of a sudden, we've got something that's helping the grid rather than hurting the grid. Very interesting observation. So,
Yeah, but most people, when they go to work in the middle of the day, they're not plugged in. I mean, they're plugged in at night when they come home. And that,
well,
if anything, that exacerbates the duck bill, load curve.
Uh,
sure. So then,
Unless you're like Eastman Chemical that has 26 EV chargers, or downtown Kingsport, for people who work down there, they've got 8 chargers down there. So there's actually a fair amount of workplace charging that's out there, and it's growing.
yeah, and that's my point. Exactly my point that you made for me. If we grow the workplace charging, that's where the opportunity is, and that's the only way we're going to make this happen during peak time between 5 and 6 o'clock in the afternoon, or 4 to 6. Is you've got that car plugged in, charging up. Well, we've got an example. Let's move on here, and we'll see what that might look like. Okay. So this means something like if we have 20% availability, that means we're going to need about 40 million vehicle to grid chargers. So there's your number. Okay, in order to make 20% availability of these things, these cars are going to have to be plugged in somewhere, and communication and stuff is going to be interesting. So let's look at what we have to do to make this happen. And is it possible? Are we too stupid? Is it too expensive? Whatever. 2022, there were 283,400,986.371 I threw in a decimal point again because I love these precise numbers. That's what we had in the United States. Half of them were owned by people over 60. You know, the guys that drive the grocery store twice a week or whatever. I thought that was a pretty interesting number. Crossover SUVs, 45% of auto sales as of June 2022. Average daily driving mileage was 30.1 miles. Okay, and you know, we've heard numbers 30, 35. Different people calculate different numbers, and then if you throw trucks in and if you throw other things in, if you talk in commercial vehicles versus personal vehicles, and you know, a lot of different ways you can change these numbers, but we're just doing an exercise here, and you can change the numbers and rerun them, do the math over again with average driving of 40 miles and see what that does to the numbers. It multiplies by 4/3. But then there's maybe some that multiply by 2/3 and whatever. Highest number of drivers in California, Texas, and Florida. Okay. So it's not unreasonable to imagine 100 million electric vehicles available for vehicle to grid. If we've got 283,400,986 out of them out there in 2022, and they'll be where they're needed the most. Because wherever you got the most people is where you got the most vehicles, is where you got the most demand. Pretty much. So that's interesting. Your storage is in the parking garage or out under a parking canopy where you work. And maybe you're going to fill it up again at night at home, or you're going to fill it up at work while you're at work during the peak hours of the day, 10 to 2, and then sell it back between 4 and 5. Who knows? Interesting. And then, of course, we got Central Time, Pacific Time, and Eastern Time, and Mountain Time. And it's not 3 o'clock or 5 o'clock everywhere at the same time. And electricity travels pretty fast if we decide we want to build some east-west transmission lines. So interesting thoughts about how we can move some of this stuff around if we wanted to. This is Minnesota talk. Okay, then. So how do we do it? Probably need a few things. We could consider equipping the existing vehicles, the V1G. That means we're just taking electricity from the grid rather than V2G, which means we're either buying or selling from the grid. But it's not happening in 2024. Nobody's really putting inverters in their car so they can sell back. But there are a few vehicles out there right now, including the Cybertruck, that's equipped to sell back to the grid. But if we were to use this inverter, we could have it either internal to the electric vehicle with the two-way AC charge or discharge. We could have the inverter external to the EV. And we could use AC or DC into the vehicle and DC back to the external inverter and into the grid. In other words, there's some options out there that people are going to think about. And we can forget about converting the older vehicles and incorporate load management to existing charging options for the older vehicles. And that means the older vehicles can help as well by charging during peak time when the electricity is available, and not charging at times when the electricity is needed for other uses. So even if you're not a vehicle to grid type machine, you still can be a part of the solution rather than a part of the problem. Because after all, we have that 40% load factor we're dealing with. So newer chargers probably will be bidirectional, or maybe at least optionally bidirectional. And then they're going to have various communication protocols for the V1Gs and the V2Gs. Okay. And this is a really good article here. Which cars have bidirectional charging, and I got some pretty good references on these slides for those who want to pursue this any further. A little more background. Here's some more EV features. The V2L, vehicle to load. My boss, who's a former student of mine, happens to have a Ford, what is it, an F-250 or something, electric. It's got a duplex receptacle on the thing where you can plug in, get 120 volt electricity to charge something. Well, like if you went on a camping trip, he could power his tent or his campsite. And it doesn't need a bidirectional charger. It just lets you power a load, and it's essentially a standalone power source. V2H, that uses vehicle power to power an occupancy via a bidirectional charge port. So you could use this as home storage if you had a power outage. Then you could plug in your car and use power from your car battery to run your refrigerator. And if you got 75 kilowatt hours and you use 3 kilowatt hours a day or so, to 2 or 3 kilowatt hours a day for your refrigerator, your car's not going to care. And especially if you got some solar to replenish it every day. V2V is vehicle to vehicle. And that means you see an EV out there ran out of gas, ran out of electricity, you plug in your extension cord and you give them a recharge, fill them up, just like going out there with a can of gas with somebody who ran out of gas. V2G uses electrical vehicle power to stabilize the grid, and it can be controlled by the utility when the vehicle is controlled to a smart bidirectional charger. And there is a subtle difference between V2L and V2H because they have to operate as voltage sources because they operate independently of the utility, so they need to be a stable 120 volts. But V2G, on the other hand, has to operate as a current source because that's what UL 1741 requires if you're going to sell back to the utility. You sell back with a current source, and oftentimes that current source will have current limiting available with it. Okay, and that means that your voltage has to be higher than the utility voltage in order to run the current from you to the utility. And your inverter adjusts its voltage as necessary in order to make sure that the current available is supplied to the utility if the utility wants it. So V2H, V2L, V2V, they don't connect to the grid, so they don't have to comply with UL 1547, so they can be a little less expensive. They don't have to be quite so fancy. But V2G costs a little bit more because it has to be compliant with very good sine waves, good stabilization and frequency and so forth. And it has to disconnect from the grid under certain inconvenient situations if the grid were to fail or whatever. So the vehicle means of contribution to this solution is essentially already solved. So let's see what else is out there that we need to find out about. Well, one thing, you have to find a place to connect to the grid. Where could that possibly be to connect to the grid? Well, how about your garage? It's already there. And it's probably got room for a 30 amp circuit. 5 kW is 20.8 amps, and typical level 2 charger is 32 amp, 40 amp, or 48 amps, depending whether you got a 40, 50, or 60 amp circuit. So for the most part, what you add, your service, you do your service calculation. And the size of the circuit breaker, if you come up with a load calculation that says your load is the calculated load, or even your measured load is, say, 120 amps, then if you have a 200 amp service, you've got a lot of headroom there. And you could put in another 60 amp circuit breaker and have a super fast charger, one that charges a whole lot faster than you need to charge. A lot of people want these things, but I don't understand why. If you're going to charge overnight, we charge with level 1 charger, plug the car in at night, but we've only got 17 kilowatt hour battery, and we almost never use all of the 17 kilowatt hours. But overnight, with level 1 charging, it's very simple to pump in 15 kilowatt hours if you need it. So these, and that's at 120 volts and about 12 amps. So, in any case, garage is a pretty good place. And of course, garage or a parking area where you go to work, park your car, equally good place. And so you simply have to follow the rules when you install the charger. And the National Electrical Code has that's very well covered in 625.41 and 42. Interactive charging is covered in National NEC 625.48. So they're all set for it. The code's ready to go. Started in 2020. It's in the 2023 code as well. And so we're good to go on that. The technology is there, the codes are there, ready to go. How do you do a load calculation? I'm going to do this very quickly here. If most services can add an extra 5.676 kW on a 30 amp circuit breaker without even needing a service change, turns out. But 125% of the charger current has to be added to the existing load to determine what size your feeder to your main service has to be. And that's normally going to be also your main circuit breaker and your bus bars and your panel. Note that if more than one vehicle is being charged, they might end up sharing. Okay, so 2 vehicles can't necessarily provide twice as much electricity, but that doesn't mean that twice as much electricity in terms of demand. However, you can certainly charge 2 or more vehicles on a single circuit if they share the charging, because if it only takes 2 hours to charge one up for what they use that day, you got 22 hours left to charge the other one, unless you're being nice to the utility and not charging during peak time. So therefore, you can charge a number of vehicles on the same circuit, each of which then could conceivably plug into a different place and share, or could share at a different time. So here's where that 20% utilization factor comes in, is depends on when the people want to charge and discharge, and whether some kind of a deal could be worked out. I mean, you kind of have a deal when you go to work, you show up by 9 and you leave at 5. And you could have a similar deal with the utility about when you buy electricity and when you sell electricity on predictable days. So in any case, you'd have to figure out some kind of a sharing algorithm, and based on that, what you buy or what you sell is based on that algorithm. few more details for connecting to the grid. You're going to have to sign an agreement with the utility. Already have to do that if you have solar or wind or anything else. Grid support is based on a number of circuits, not on a number of chargers, because you can have more than one charger in a circuit if they talk to each other. So this is like in a condominium like I live in. We could charge every electric vehicle in this building if we had all electric vehicles with a single. We have 43 units, and we could use, I figured it out, a 225 amp three-phase circuit could charge every single one of those at more than 100,000 total miles available a day of charging. So it's not as bad as it might sound. And we have more than enough headroom in our main 800 amp service. We're only using about 300 some amps of our 800 amps right now. And we got plenty left over to charge electric vehicles. V2G is part of PV system with backup. Interesting stuff. You can give priority assignments. Substations are going to be really important, and our host has a very interesting webinar on substations. Grid stabilization response times would have to be less than a second, and preferably less than 100 milliseconds. When you make the connection, you need to establish your buy-sell conditions. And if the vehicle is to be disconnected by the owner, the utility might appreciate a little advance warning so they can take that into account. Site preparation, pretty minimal if you got the garage there anyway. So, basic charger connections. Let's take a look at some of them. Here's pretty basic. You just connect your charger to a circuit breaker and charge your car. No communications or anything. Actually, that charger is probably going to have something that connects to your cell phone that tells you how well your car is doing. But there's no charge limiting or anything, but we can improve on that. If we add some load management by putting a current transformer in here, we can say, wait a minute, we are not going to charge the car if we're pulling too much current from the utility. And that can be some kind of an agreement with the utility that says, hey, this is a bad time of day to be charging a car, we're going to cut back. So one little current transformer solves that problem. It's a little bit more sophistication in the charger, but that's all circuitry that's well established. We can add a renewable source. And a lot of folks have these. And then we can say, well, as long as we have that renewable source, why don't we tie that into the system so that we will only charge when the renewable would otherwise be selling back to the utility. We're going to put it into the car charger instead. And once the car charger is full, then we'll let the renewable source sell back to the utility if the utility wants it. Unfortunately, if it didn't, that would mean that would have to be curtailed unless it could be stored someplace else. And then we could add some communication so we can talk to the utility and make these arrangements. So that's a pretty basic thing, and then you can go from really basic to a little more sophisticated without a whole lot of extra technology.
Roger,
Yeah.
have you done any research or do you know anything? I thought if there was a smart vehicle charger that just sensed the frequency of the grid and could, either ramp up or ramp down depending on frequency. And that would give the utilities a really big knob that they could relatively easily adjust without a lot of communications, just by kind of allowing the chargers to follow the grid frequency.
Exactly, and with the V1Gs, that's a really good way to do it. We're going to see what some of the folks are doing, and there's no one right answer here. What you suggest is certainly a possibility, and it probably happens. That's what That's what happens with additional sources. When the frequency starts dropping, especially with photovoltaics, when they notice the frequency dropping, 1547 in 2018 said, wait a minute now, the last thing we want is a 300 megawatt photovoltaic system to drop out just because the utility frequency drops down below the level of, required in IEEE 1547. Because you need that. If you let your photovoltaic system drop out, then your frequency goes drop even further. So what you say is exactly right. It's a very straightforward way of knowing when the grid needs it and when the grid has extra. So, very good point. And here's here's a little fancier one. A lot of folks have these in place right now, not necessarily with the V2G charger, but with the V1G. They've got renewable source, photovoltaics. They've got batteries. They've got a distribution panel, a system controller, communications. Excuse me. I swallowed something but down around 2 at lunchtime, and it bothers me a little bit here. So anyway, this is a possible connection and a highly likely connection in another 10 years. If in fact, unless somebody finds some better way to do it. But this is certainly right now a way that can be done, and we have all the tools we need to do it. You need a buy or sell interface. And one way to do it is like this. In other words, in the car has to know whether it wants to deliver electricity or receive electricity. And AC is going to go in and out the same plug. And if that's, that's interesting when you realize that the machine has to decide whether it wants to send it out or bring it in. If it comes in, it's going to be rectified into DC. And this EATS, the electronic automatic transfer switch, is going to be in the up position so that it will be charging the DC storage pack. But the DC storage has got all kinds of monitoring of temperature and everything else. Just like your cell phone tells you when it's 100% charged. When it's 100% charged, it shuts off. Same thing here. When we get 100% charge in that storage, it's going to flip that switch down so that now it doesn't want to charge anymore. It will either discharge into, and of course on the other side of this is running the car, but this is on the charging side. There's one method that is out there and doable, and the technology is well established.
Well, I think that, bidirectional inverters are you don't need a transfer switch. I mean, it's all has the electronics are all built in. It's just a matter of the microprocessors that control which IBGFs fire will do the inverter. You don't really need a switch or anything like that.
Well, this switch might very well be an electronic switch.
Oh, I mean, it's not a switch at all. I mean, it's the same electronics. You're just going through
It's the
different
same
paths.
electronics. The point is that the electronics decides whether the electricity comes in or out, which technically speaking is a switching function. So this is just a schematic. And yeah, a lot of this stuff we've probably done electronically. I'm not suggesting this has to be a mechanical switch in there, but there has to be something smart enough to know when to buy or sell. And it doesn't necessarily have to buy or sell when it's full or empty. Yeah, it could well say that when I'm up to 80%, I'm willing to sell if you want me to. So you give me a signal and I'll sell it to you. And this is geared up to do it. And again, like you say, probably done electronically. But it's kind of easier to understand a little switch like this rather than see a bunch of MOS power transistors or something in the circuit. In any case, communications are pretty important when you're starting to do this electronic transfer switches because the system needs to know if it's time to sell or time to buy. And what about utility equipment? Well, they are communicating with stationary storage sites already. So installing EV charging stations, they're kind of stationary. So fact of the matter is, the estimates is that there will be more investment in EV charging stations and the accompanying management systems in 25 than in solar systems. That's interesting because there's a lot of money going into solar right now, but even more going into EV charging stations. So that's something that was brought up earlier. And this is where Wall Street likes. That's where the money's going. Where's the control going to be? It can be at a microgrid level, small neighborhood thing. It can be at a higher level. We have to decide charge management protocols, status, charge time, charge rate, purchase price for charging, best time to charge, all kinds of things you can include in that protocol. There's ISO 15118. That's the standard protocol that's becoming a leading global standard between EV and charging stations about charging opportunities. Whether it's charging available, how much charge you can get, how long, and so on and so forth. I've not used these. I generally just plug in at home. But in any case, this is out there. The standard is out there. IEEE 2030.5 covers distributed energy resources. What does CSIP mean? We have a reference to that here in a minute. SAE J3072 is out there. Continuous service improvement process. That's what IEEE 2030.5 is. So this quality logic people, read some of their stuff. They're really up on top of it, doing some really interesting stuff. When you talk about communications, they're not just messing with whether or not the frequency is up or down. They're looking at a whole lot more than just that. They're looking at substation and what kind of currents are flowing in those transformers. So might as well have a few more acronyms for the dinner table. The DR, that's demand response, and then there's a demand response aggregator. We'll see what that is. Then there's the open ADR, and then there's the distributed energy resource, and then there's distributed energy resource management system. And this is generally at the utility level. Then there's a charge network operator, which can be a robot, could be a person, maybe some combination. Energy management system at a building or microgrid. Lots of energy management will be happening. Lots of really interesting stuff is out there for energy management as we speak. Open charge point protocol is pretty common on every V2G charger. We've got it on ours, and ours is a pretty baby thing. So how do you use these acronyms? What are these little blue things over here on the right-hand side anyway? Are they raindrops? No, they're car tires. Why, the red car is the V2G. That means it just takes electricity from the grid. The V2Gs, they'll go both ways. And they get it from a charging station. This is a charging station at work now, okay? Our imaginary charging station at work. And it's going to talk to these things and then bidirectional or just one-way charging. But the V2G vehicle might say you can have electricity now, but you can't have it later. So take it now when we have it and be happy. So there can still be that communication taking place there on that vehicle. And of course, there's not only going to be one charging station, there's lots of them out there. And so when you've got lots of charging stations, somebody has to talk to the charging stations. Who's that going to be? Well, how about the CNO or the EMS or somebody else like the aggregator? In other words, they're the guys who talk to the charging stations and tell them what they should be telling the vehicles they're charging. And they have their communication protocol. And the reason the arrows are different colors is because they're actually different communication protocols for these different links. I'm going to take a look at those in a minute. And what about the aggregators? What are they connected to? Is there only one of those? No, there's lots of aggregators too. And they report to the utility distributed energy, distributed, the DERMS. Again, tongue-tied here. And notice they've got a little orange communication out to the aggregators, and the orange arrows are open ADR. That's the protocol. And I don't know what it is. but they got it. And the guys who know about this stuff know what it is. And OpenADR or Open Charge Point Protocol is there in those lighter green or darker green between the CNO and EMS and the charging station. And ISO 15118 and then a couple more of these acronyms are the protocols that would be used between the charging station and the vehicles. I really like this picture. I don't know about you guys. I had fun drawing this thing. And this we can thank Quality Logic. And if you want to learn more about what's going on here, just go to this website for Quality Logic. These guys are really seen to be on the ball. That's where all this information came from. So here's your car plugged in. And we do a little car talk in honor of the well-known, famous, previous Once Upon a Time Saturday Morning National Public Radio show. Here's the car. Hello, this is vehicle number XYZ. And as you can see, my state of charge is 50%. So if possible, it'd be really nice if it'd bring it up to 90%. If it's possible, what would you charge me? And that's something that happens in about a millisecond. You send that message in once you plug in. And the utility comes back and says, oh, yeah, you plugged in at a good time. It's 11 in the morning, lots of solar coming in, got extra capacity, and we can sell you this electricity that you need at 12 cents a kilowatt hour. How's that sound to you? And we can charge you at 7.6 kilowatts. Will that work for you? And the car says yes or no, and we'll assume the car says, well, 12 cents, geez, that's kind of expensive. Can you do 10? But let's say 12 is agreeable because the car says, well, yeah, sure, charge me up. I can go for that. If I plugged in at home, it might cost me 15, so well, why not 12? And then a little later on, vehicle says, okay, guys, I now have sufficient kilowatt hours to make available a certain number of kilowatt hours, like 10, at say 5 kW until 5 o'clock. If the price is right, well, okay then. Oops, I'm slipping into Minnesota talk again. I guess that's where I grew up, and I can't resist it when I get excited. So then what happens with the oil utility says, well, we'll take that under advisement. What would be your selling rate? If I got to move something out of here. Okay, if we need the boost, then on goes the conversation. This is taking place in like 100 milliseconds or so after plugging in. And as long as the rate is satisfactory, they go for it. And if the utility needs it, fine. If not, the car's charged to drive home that night. So anyway, this is the kind of communication that will likely take place. Maybe not, who knows, but it could. What's the bottom line? Well, Quality Logic presents an XV1 overview. So if you want to go there, here's the name of their thing and here's the website. So check it out. Interesting stuff. Again, this is their idea, so I've been showing you. Not mine. I just thought it was a pretty good idea. So how about the cost? This is the real clincher. What's it cost? Well, a 5 kW inverter should be available for $1,500, give or take a few. The transfer switch with communications, 500. Bi-level directional charging, who knows what that's going to cost? Good question. And for that matter, it's probably just a marginal cost between the bidirectional rather than the one directional. So what is that going to be? If you have solar with it, then you've got the options of V2G, V2H, V2L. We talked about that before. And quite a bit of the PV equipment, we're seeing a number, Enphase has, Tesla has the equipment that's already well equipped for doing load management. in terms of vehicle charging. So that's out there with solar, and it's software, so it easily change from V1G to V2G, for example. For a new vehicle, it's the marginal cost because either the vehicle or the charger well, the vehicle actually has to be equipped for V2G, and the charger itself has to be equipped for V2G, and of course the two have to match. So there's a little standardization that probably needs to happen. So, cost. This is a fun one, the levelized cost of storage. Thank you to National Renewable Energy Labs. They have a very nice formula, looks just like this. And no, I'm not going to try to go through that whole thing, but basically we're talking about what is it, the project cost minus the value of any residual after the project comes to an end, after the life of the life, what is the salvage value, plus whatever operating and maintenance costs, corrected for the time value of money, divided by essentially the total number of kilowatt hours produced over the life of the system. So you're getting $1 per kilowatt hour. And that's how much you're going to have to charge for this electricity you sell in order to pay for your storage. Simpler way to look at it is simply saying the levelized cost of the storage is the cost of the system divided by the lifetime system kilowatt hours, with a few little corrections. For example, 10 kilowatt hours for $10,000. That's kind of about what they're going for these days. If you have 10,000 lifetime cycles, and that's kind of what the warranties are saying, then you can get 100,000 kilowatt hours. That's 10 cents a kilowatt hour. So therefore, you have to sell your kilowatt hours for 10 cents plus whatever you bought it for in order to pay for your system. Now that's if that's all you're going to do with the system, but if this system also provides an insurance policy for your refrigerator during times of utility outage, then some of these numbers don't mean quite as much anymore. So anyway, and by the way, this is a pretty simple example, but if you look up levelized cost of storage, you can look up some incredibly complex diagrams on the internet. I looked at it just for the fun of it last night, and some of the diagrams are incredible. So if you're really seriously going to invest in it, you'll probably look at one of those. But this,
The complex diagrams are because the complex calculations are because the formulas are using batteries where discharge rate and charging rate and also the life of the battery is only 10 years, all factor into those numbers. I think if you were like looking at the calculations for like a pump storage plant with a 60-year life span, this calculations are a lot simpler.
yeah. So that's the point, that this just gives conceptual idea. But if you want to get serious about it, you go in and you look at the lifetimes and look at a lot of other numbers that fit in the picture.
And
So
I was going to say, I think the life is actually longer because the warranty is 10 years. And, like my RAV4 Primes had a 36,000 mile, or I mean, a 50,000 mile drivetrain warranty, but I expect it's going to last much longer than 50,000 miles. Also, and like the Franklin whole home has got a 12-year warranty, and their new stuff comes with a 15-year warranty. So I think there's a lot of data that says that the batteries are going to last significantly longer than 10 years.
yeah, exactly.
That's the calculation for utility batteries, which are installed on huge racks, and I believe the warranty is 80%. You can still go down to like 80%, and so you're definitely talking even in terms of the warranty. You meet the warranty as the batteries degrade, and again because utilities they charge and discharge a lot more than a driver would under normal conditions. It's a lot more rigorous. It's a lot harder on the batteries.
And it's also interesting to note that I think it's in North Carolina where the utilities are using the used batteries from hybrid vehicles and other electric vehicles where the batteries are no longer useful for the vehicles because the internal resistance is too high. But in terms of the rate of discharge utilities need, they're perfectly good. So just then move it from the car to the permanent storage and utility and then get, however many additional cycles out of them with simply a little bit more losses, a little bit higher internal resistance as the battery gets older. So yeah, I mean, some of these things are still yet to be proven. I don't see any evidence of degradation in the batteries in my car at 7 years and 35,000 miles. And but then again, you look at the manufacturers are now, rather than saying the number of cycles, they will give you the annual or the expected lifetime kilowatt hours that you can deliver from the batteries. Quite a few of the manufacturers are doing that now. So forget about years. It's lifetime kilowatt hours that they're tending now to guarantee put their warranties on. And again, that's a matter of how you use your batteries. If you're nice to them and discharge slowly and charge slowly, then the batteries are a little bit happier.
Well,
So, there's so many factors, and that's why the chart's so big and so long and complicated, because if you take all that stuff into account, then the simplified form is just exactly that, a simplified form. But it's a way of at least thinking about it to get the ballpark that, hey, yeah, this is maybe worth looking at some of the other numbers because 10 cents is not that bad of a number. So, and then the other thing is just the round trip efficiency. You'd have to have 11 cents if you realize that you have to buy 10% more than what you be able to sell back. So, in any case, just a quick number so that we've got it handy. And this formula comes out of National Renewable Energy Labs, and there are people who've taken this formula and they beat it to death in terms of all of these anticipated degradation rates and things like that. And the whatever they imagine the time value of money might be and the discount rate. That's what the DR is, the discount rate. And we know that's pretty unpredictable. It was down there right around 0 for a while. Now it's up around 4 or 5, whatever it is, I'm not sure. And it looks like they're trying to get it go back down to 0 again. Hard to tell, but we'll see. Um, so anyway, this is just some of the math that people are using and thought you all might like to see what it looks like if you haven't seen it before. We can do a simplified example. If day one, we'll start charging at noon and we buy 10 kilowatt hours and we sell 9 because we can only sell 9 out of 10. And so at 8 cents a kilowatt hour, it costs 80 cents. And if we sell it for $2.25,
whoa, that's a big number. That's
well,
that's that's
you are
that's over
peaking electric.
$200 a megawatt hour. That's
No, no,
I mean,
well,
that's
yeah,
the
but
problem with this whole scheme is that we're buying you're supposed to be buying energy at a wholesale price and then selling it at retail, but this is exactly the opposite. This is buying retail and then hoping that the utility will pay more for it.
well, retail at 0.8, and then the buying cost. Look, if you buy at a different time, look at day 2. We're buying at night and pay 40 cents for it.
Yeah,
And we sell it for
it's
270. Again, this is just a
these
matter of
are
what
numbers.
month, and when are you selling it? And not every day you're going to get that price. And the peak time, I have seen numbers of peak electricity costing over $1 a kilowatt hour when they are really stressed out.
But that's not very often.
Not very often. No. The
The
point being
thing
that, but
that's
for a standard replacement source, 25, 30 cents kilowatt hour for
this
say a turbine, that's not too unreasonable because it's going to be uh, have a duty cycle of maybe 10%. So they have to sell for a pretty high price.
now
But it's
I'm
what
I'm
keeps
only
it
I'm
up.
only familiar with New York State, so
Yeah.
they have the New York ISO, and then there's within the New York ISO there's probably about 20 different utilities and suppliers, everything from little munis to larger utilities.
Good. Of course,
And
that's a
then
good thing
they've
about
broken
ISO.
down, the state has, I think, 40 zones, something like that, where the price in every zone, you can go on the web and you can find the different zones.
Right.
And there's 40 buses and maybe like 10, 15 zones. Prices are all over the place. I don't see any reasonable way that, just an everyday driver is want to go into business, so he can make, a few dollars a day. And the build out for this, the communications and the studies and everything that would be required it would be astronomical for not very much benefit because I've worked on a battery energy storage system that was put in a transmission constrained place. So in other words, it went the place where in New York State the price would actually go negative because they don't want people to generate because it's going to overload when the wind's blowing, overload transmission lines. So they were able to buy negative and they would sell at a better rate later. To buy it
Right. Right.
retail is nuts. And then have the utility buy it back is nuts. They have so many other cheaper sources, ways to provide that energy. Uh, what may turn out to be is like what they had, years ago. They put timers on water heaters so that you would not be heating water in peak days, and it worked sort of okay. And then
Oh,
they
yeah.
also put water heaters that would have receivers on them, and they were using transmission not cell phone, pagers,
Yeah.
remember those
Yeah.
things, to turn the water heat. And basically, they never really worked. I mean, they didn't, the timers
Yeah.
would go
Well,
off.
yeah. Water
They were
heaters,
all abandoned. Those systems
cool
were all
pumps.
abandoned.
Yeah. Water heaters, cool pumps, air conditioners. Turn them off for 15 minutes and we'll give you $3 a month discount on your electric bill.
Yeah, something like that would
That's what
work.
we had
Um,
here in Pittsburgh
I
back
don't
then.
see trying
John,
to do
but
frequency
John,
regulation.
there may be a
So,
middle ground, and that is, if electricity is high during the evening, let's say it's 60 cents a kilowatt hour, but in the middle of nights it's 10 cents a kilowatt hour. I could see a lot of people using their cars to kind of charge up at night when it's cheap. And then when energy is expensive, at least use it in their house. Maybe not selling it back to the utility, but that way the utilities could sell more during their low demand times and they could do some peak shaving because a lot of people will be self-supplying during the peak pricing times.
Yeah,
yeah,
but
I mean, that's what
there's a
everybody's
tremendous
saying.
infrastructure to
Time of use
do
is
all
what
that.
yeah, time of use is what it's all about. And so you get locked into the time of use thing and you try to fit into that picture. And again, this is a simplified example. May or may not happen. But if it would happen, and when you look at utility generation curves and so forth, you can see that it's feasible.
Right.
But,
And
but it's
John,
not
you
worth
talk
it.
about
And
the
clearly, when you've got
infrastructure.
excess electricity and you don't want to curtail, then your only option is storage somewhere.
Yeah. And John, anybody who has a solar system and an EV charger like I do, the infrastructure is already in my house. So there's millions of people already having that infrastructure and it's growing.
Okay, the infrastructure is there. How it's used is something else. I mean, the issue with battery storage and we requiring a lot of battery energy storage systems is not just for, load shifting. It's to be able to provide that fast response, for disturbances. I mean, we talked a little bit about it, with the saying the frequency response, building it way down to the charger. But utilities, when they're running their system, they're constantly doing studies and they're constantly making setting changes to the generators to what their frequency response is going to be, depending on the actual state of the transmission line, what services are out, what generators are out. I don't think they're going to really appreciate a frequency response that's, dependent on basically how many people have their cars, charged in. That's the one thing. Also, what the battery energy storage systems are also required to provide fault current, during faults to prevent the voltage collapse. You're not going to be able to do that from car chargers that are way down in the distribution if you have a fault, way up in the transmission system. So for
But
those,
what they
but you don't
can
get any
do,
of those benefits with this scheme, as opposed to just building battery energy storage systems, putting them where they're needed, putting them where they're the most benefit, having a control system in it that you're able to model. I mean, one of the issues in Texas where they've had a bunch of near blackouts due to their is that a lot of times a lot of these different inverter manufacturers, they have different software. They give them the parameters to the utility to be able to do their studies, but then in real life, because the software is all different, the software changes. In real life, it doesn't really match. The actual performance doesn't really match what the parameters show in the utility models. It just seems like this is a lot of work for basically it's just load shifting. So, if you're doing it, yeah, if you can do the load shifting by charging your car when your solar panels are that's benefit for you. I don't know how much of a benefit is for the utility. But like I say, it's good to have, but its benefit to the utility and the people who have to operate the utility is kind of limited. And really, the solution really is, large scale battery energy storage up on the transmission system. I mean, the they had the Iberian Peninsula blackout. I mean, their whole system collapsed in 6 seconds. So you need that fast response, at a large scale in order to prevent that. So just saying, not to rain on anybody's parade.
well, this is the people who believe in this are going to do it, and the people who don't won't. Very simple, and we'll deal with it however we have to deal with it. I personally would prefer to have my own energy storage at my own location if there's a utility outage, because
Yeah, that's fine. I
I
mean, there's
can't
there's
get
plenty
that
of
power from
opportunities
that
for
big,
that.
powerful energy storage system in North Florida. If the transmission is down or the distribution is down. So there are certain advantages to having some storage in a localized
Yeah,
location
yeah.
and even some generation in location.
At my
But anyway,
son's
we're
house.
we're pretty
Mhm.
close to being out of time here, guys. So we gotta let's finish through the slides, and then if there's any time left over, let's talk some more, okay? Um, Time of use pricing for buy and sell, 10 kilowatt hours a day, V2G. We're trying to look at how long the batteries are going to last here. So 3,000 days. You have about 400 cycles of 3,000 cycles would be used for V2G. Okay, because we're not using a full cycle. 10 kilowatt hours a day is not a full cycle on the batteries, not for 75 kilowatt hours. It's only 10 over 75 of a cycle. So therefore, you're using 400 cycles out of the 3,000 cycles presumed guaranteed lifetime if it's guaranteed in cycles, and that's a conservative estimate, as was mentioned earlier. And another 10 kilowatt hours a day used for driving, and so you got 35 miles a day, equivalent of electricity, which you hopefully buy off peak because we're using time of use pricing. And if we have the cross-border controls in place, the utility won't sell you electricity when they don't have any to sell. But when they have additional to sell, they sell it to you at a good price. And it makes everybody happy. And it helps stabilize the grid. Um, in any case, you're getting extra 400 cycles out of 3,000 cycles that you use for driving. 35 miles a day, 12,075 miles a year, pretty close to what we've been talking about. 3,000 days, that's 8.2 years. So, in other words, if you can make $2 a day for 30 years, that's $21,900, which kind of pays for what your investment might have been. If you don't make $2 a day, you only make $1 a day. Maybe it's not even worth it. Maybe you don't bother. Maybe it's not worth it to the utility. Some people will take up on it, and others will just decide that they're going to use the vehicle to home or whatever, simply to have backup for when they lose power from the utility. You know, because one thing we haven't talked about yet is transients. We just lost a stove from a transient, and all the electronics and National Electric Code is requiring everybody to have transient suppressors at their surge suppressors at the service entrance as of 2020. So interesting things there, and that's another story on storage and where storage can come in helpful. Let's look at some other options. You got standby power if you just have a vehicle at home and a transfer switch in place. A lot of people have that now. Not necessarily with the vehicle to home, but they have their Tesla power walls and their batteries from half a dozen or more manufacturers that do this. Vehicle to vehicle charging instead of a tow truck, that could be handy. Additional standby power using vehicle to load. You got an outlet in your vehicle that you can plug in if you want to turn on your drill charger or if you want to just run a microwave oven to cook your meal if you're camping and you don't feel like building a campfire or whatever. Nice remote power source. Then again, some folks are concerned about the environment if fossil sources are replaced by renewable. What's this? What is this? Storage of renewable energy for grid. Oh, that's for grid support. I didn't spell that word right. There's another typo I've got to fix. Okay, that means grid support. Okay. Anything else I missed here? What else might there be a benefit or a disadvantage for any of this adoption of electric vehicles?
Well, I think the time shifting, kind of at least using your own power when you can, when the prices are high, and filling your car when prices are low.
Okay, so we can add that. And anything else? Well, I'll invite you to think about it. There might be other good or bad things about it, and you can put that down on comments. Like I say, this is the first time we've presented this, so it's not necessarily all inclusive, and some very good points have been brought up in terms of the utility perspective. And utilities, everybody knows they don't like rooftop solar, and I happen to like rooftop solar. I think there's some good benefit for the utility with it, and I think this pricing has to be done accordingly. And I also have this concern for the planet and the environment, and for my children, my grandchildren, my great-grandchildren, that I'd like to see taken care, who I would like to be seen taken care of and inherit a decent planet. So there's certain things electric vehicles have to offer for that. And nice clean electricity helps a lot for that. What if we don't do it? Let's just look at one picture here. This is pretty interesting. 2019. This was reported in the Scientific American. What happens if we meet the Paris Climate Agreement? And what if we don't? Look at the United States. If we meet it, per capita gross domestic product by 2100 drops by about 2%. If we don't meet it, per capita gross domestic product drops somewhere around maybe 12%. China, not so bad. European Union, not so bad. Interesting stuff. But this is per capita gross domestic product. And this is done by the guys who do numbers. I mean, it's not engineers doing this work. This is economists doing this work, and taking into account clean energy versus less clean energy, and what will we pay for things like as we burn our forests. Uh, then we don't have as much absorption of carbon dioxide. We're already generating 7 to 8 times more carbon dioxide than can be sequestered in a at in at the than can be sequestered. So we can't keep doing that. Seems to we're finding out the results of that. So anyway, there's a dollar cost according to these guys, and Scientific American published it. They're pretty reliable publication. So anyway, it's interesting stuff, and there's a lot yet to be determined. And who knows? Maybe we are at the dawn of a new era. Good question. It is 4:01. We've taken up exactly 2 hours so far. If anybody has want to add something at this point, go ahead. Let's talk. I'm sure that Hisham will give us at least 3 minutes if we want to have a little conversation.
No, good course. I just agree with most of what you say.
Well, that's not half bad if you agree with most of it. I mean, I can't say I agree with it all. I mean, a lot of it, I mean, it's conjecture. And it's a matter of if we do it, what will it cost? And basically it says we could afford to do it if we had the will to do it. We will, maybe will or will not, or maybe we'll find a better way. We'll see.
Roger, Kelvin here. Good course, and I almost didn't take it because it is advertised as electrical, but having worked in the power industry for 40 years, and it, 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 there's a lot of good information here on energy conversion. So maybe you want to extend it to add mechanical as part of it.
Yeah, I mean, mechanical and civil are essential parts of green energy.
Right, right.
No question
Especially,
about it. Can't build
especially
a
I
solar
have
farm
plenty of
without civils.
yeah. I have plenty of colleagues that work on, on control rooms and project managers in the power industry, which are mechanical, that they will certainly benefit from this kind of talk.
Well, mention it to him. I'm sure that Hisham will try this again another month or another maybe 6 months or so. And you can share your slides with them if you want to take if they want to take a look at them.
Sure, appreciate that. Thank you.
Well, okay, if there's if this looks like this might be it.
Oh,
Oh, another
I
thing.
don't know, little help on the very first question. If I recall, do we go on your slides or the corrected number on the amount of renewable on our grid in 2025 when you include the hydro?
Yeah, you can go with the corrected number on that.
Okay,
Yeah, I mean these are supposed to be not exactly order of magnitude, but there's an equal sign and then there's an equal sign with a little squiggle about it that means about equal to, and we've been making those kinds of educated guesses on how many miles a year. And the point is, it's not necessarily where we are right now, but what is the trend? I tend to look at the derivative, the slope, and what does the trend look like? And to me, from a worldwide standpoint, just based on the economics, the trend for this kind of technology looks like it's moving pretty quickly. Oh, and by the way, buying electricity, my grandson has an electric vehicle, but and he's an engineer, And he's on time of use rate, and he pays about a nickel a kilowatt hour for his electricity, so he drives pretty cheaply. I think he buys it between midnight and 5 in the morning or something like that. All right, well, thanks, folks, and I hope you have an enjoyable.
So how does that? That's just his rate. So it's really up to him to determine when his charger goes on, right? Because I know when my son
Oh,
had his Tesla, he could program it for, when to start charging, when to end, and how much to charge. So your
yeah,
son,
yeah, same thing for my grandson has a Tesla,
okay,
and
so
that's
he
what
has
he
to
does.
do it himself, though. It's not controlled by the utility. The utility just provides the price, which is
Well,
just a
yeah, right.
download to the
So as
meter,
long as he buys it when the utility wants him to buy it, then he gets that price.
right?
And that's why he's buying it between midnight and 5 in the morning.
Right. But that's a simple
That's
download
in
for,
Minneapolis.
right.
This is a regional thing anyway. It's different
Right. But
utilities have
that's
different.
a simple download to the meter. That's not the same thing as saying when the utility needs it, they want to call for it. So,
No, no, of
okay.
course not. And here we're not talking about the utility needing it and calling for it. Here we're talking about the utility having it and being appreciating that you're using it. Okay, we're all set. Thank you, gentlemen, and have a great summer.
Thank you.